I would like to introduce you guys to our very next speaker. His name is Mark Gamble. Mark is a product and solutions marketing director at Couchbase. He is a passionate product marketer with a technical background of over 20 years in enterprise and open source technology. He loves all things data and is an empathic supporter of Data for Good initiatives. Today, Mark is talking about the right stuff for really remote edge computing. Please help me welcome Mark to the stage.
All right. Thanks, everybody. No, I don't normally wear this every day, but I love what they did with my picture, so it had to come out. But now I can actually, see you guys. So I'm going to talk about edge computing today. But first, a little bit about this talk. I actually gave this same talk at the AWS Community Day in Chicago. And it was really good. The program was fantastic. The venue was great, but not like this. Vancouver, you guys really brung it. I mean, this is just amazing. What an amazing place to actually be able to speak. So it's a real big honor for me to speak to you guys today. So Couchbase is a NoSQL cloud database platform with particular strength in edge computing, mobile, and edge apps, be they AI-powered or otherwise. It runs on AWS as a managed service. It's hosted, but it can also be deployed self-managed. That means you can deploy it wherever you want, on-prem, on your own AWS instance, and you can even link the managed hosted with the self-managed. And I'm going to talk about, of course, edge computing. You know, a lot of the program here is going to be about AI. We can do AI as well. We're a vector store from cloud to edge, but AI is most powerful when the consumers, the users, can actually see it, right? So we're going to talk about reliability and speed of applications. And when edge architectures are appropriately applied, they can really enable highly resilient, fast applications that work everywhere all the time, regardless of internet connectivity. So let's dive in. I'm going to be talking about, of course, edge computing, and then the Ask stack. Maybe not the best name, I came up with that, but it's the combination of AWS, Starlink, and Couchbase to actually create this infrastructure that's impervious to internet slowness and outages. And then we'll talk about latency and bandwidth test results. We actually put it to the test to see how it would actually perform. So now let's dive into the notion. First, I'll set up a couple of problems. Because when we talk about really remote, I'm not talking about the top of Mount Everest or the middle of the desert. Of course, those count as well. But really remote can really qualify as anywhere that you have no connectivity. So consider an offshore oil platform in the North Sea with 3 or 4 control room operators that are continuously fed data from thousands of sensors that are running all over the platform. And operators have to control a multitude of variables, each with different settings. And at the same time, they have to consider things like temperature and pressure and wave height and wind speeds, these kind of things that can affect the operation of the actual platform. And there's so much information that comes so fast that operators actually have to slow down production to reduce risks and hazard. There's a McKinsey study out there that shows most of the oil platforms operate at about 75% of capacity because they can't keep up with the data. And imagine if they could operate at higher capacity, what that might do to our gas prices. So this really becomes a barrier to efficiency that companies just can't overcome, especially when their on-platform applications rely on data and AI in the cloud. So suppose you need to analyze, critical warning data from a pressure sensor. And if that data has to be pushed all the way up to a distant cloud data center, maybe through a geostationary satellite, that's very slow, very costly, and by the time you get back an evaluation of what you should do, it might be already too late. So what's needed is a way to keep up with this deluge of data that happens at all times on the platform without relying on the internet. So next, let's consider an airline. By the way, these are anecdotal of all of actual customer cases. So let's consider an airline where great customer experience is really the difference between loyal customers in a packed market and dissatisfied customers. And it requires providing a personalized experience for passengers and making onboard processes as fast and efficient as possible. So to do so, it's imperative that cabin crews have fingertip access to the information on each and every passenger, ideally, and that they can always know the current inventories for things like meals and duty-free goods and items so that they're never selling things that are already sold out. These kind of things can erode kind of that customer confidence. And essentially, that's the key to delighting passengers and turning them into loyal, repeat customers. But if the data that holds the information is in the cloud, we've all been there trying to get connectivity, even when you pay for it on the plane. Is it ever fast? Is it ever reliable? Not so much. So how can an airliner provide a personalized experience for passengers without reliable network access? What's needed is a way to access that passenger data and inventory without relying on it. And then finally, let's consider a cruise lines that wants to enable hyper-targeted marketing through on-vessel applications. Arguably, cruise lines are a big upsell opportunity for the cruise companies. A lot of people pay in full, all-inclusive. So it's up to the actual cruise lines to try and upsell. Let's get that special amenity or that special premium wine that's not part of our free or prepaid list. So these kind of recommendations can lead to tremendous upsell. But the concept relies on the ability to capture guest data at all times and to know where they are, what they're purchasing, what they're doing, where they're going. And the problem is the guests are all at sea, where the internet is slow and unreliable. And they're all moving around the ship. And the ship is moving around the ocean. So it starts to become a real challenge to power these type of applications under these type of conditions. So what's needed is a way to process and react to changes in guest data in real time, leveraging AI and leveraging just traditional type of applications. And you need to do that without relying on internet connectivity for these type of experiences. So these cases represent a growing class of applications that absolutely require 100% uptime and real-time speed guaranteed, regardless of internet connectivity. And edge computing is that's the way you actually can achieve that. So the goal of edge computing, as we see here, is to bring data and compute to the near side of the network, closer to the application of the users that consume it. And to do so, you need to do things like embed a database to edge clients where it makes sense to do so, and embed lightweight AI models to clients at the edge where it makes sense to do so. And this model, and then also you need to make sure that you can sync data from the edge to the cloud for consistency and integrity. And the model speeds up apps because data doesn't have to travel all the way to the cloud and back in order to, evaluate that information and to supply the data to the application. And it makes them more reliable because local data processing removes internet slowness and outage from the equation. And it also handles privacy better, right? This is paramount for especially AI these days. Because in the edge computing model, sensitive data never has to leave the edge. And this is really important also about lessening the load over bandwidth too. There's more efficient bandwidth usage through edge computing because you don't have to essentially push all the data all the time from the cloud to the edge and back. And that's important when on shared networks. So let's actually dig in a bit deeper to how edge computing gets around these challenges by going through some diagrams here. So here's a simplified cloud compute architecture. In the cloud tier, we see a web application and a database deployed, let's say, in the US West region. And we have a client in San Francisco, let's say. And it could be any edge device. We're just using a mobile phone here for the sake of argument. It could be an IoT device, a tablet, custom ruggedized device, you name it. And in the cloud model, the client accesses the application over the internet with all of its inherent hops and unreliability that just comes with the territory. If the internet slows or the data center becomes unavailable, apps suffer latency and downtime, right? If you're unable to make that connection, you get the spinning wheel that we all hate to see so much, especially when we're just trying to get that Uber or hit send on that email, right? So all of these limitations can really present barriers to meeting requirements of a modern mobile application. So let's build out an edge architecture here. So in this case now, what we're seeing is additional layers of compute and networking. Here we've introduced an edge zone in the middle as an intermediate tier. Let's say in this case running in the city of San Francisco. And we've also added a personal area network in the client tier here at the bottom. Let's see how these layers can now work together to make apps more reliable and faster. So first what we do is we duplicate the web app front end and database into the edge node here. And then we redirect the client to the web app and database running at the edge. And then from there, we can connect the databases through synchronization. Okay, so we connect the edge data center and cloud DC through synchronization. All right, that's a very basic edge architecture. We've started now to eliminate the internet as a problem here. If any apps are accessing the edge node, they're unaffected by any upstream downtime. If this is a global app, we want to actually make it available across multiple cloud regions, and we duplicate the original regional zone and edge zone resources we see here, let's say in the east. And then we duplicate again, just building out the house here, from the original region over to the new region. And it's all the same data because it's all synchronized. And then we connect the databases in the middle via replication. Okay, so I'm talking generically now. But of course I'm leading to some fundamental capabilities of Couchbase. So now I'm going to make things a little more interesting. I'm going to introduce a new city in the client tier, in this case, Los Angeles. And suppose, unlike San Francisco and New York, this city doesn't have an edge computing region, even though with AWS we know it does. And in these cases, the client can still connect to the West Regional Services Database, right? So that this is becoming an actual edge topology. But let's go even a little bit further, make things more interesting, and introduce a couple of additional clients in Los Angeles. There we are. And another way to solve for edge computing is by putting the database directly on the device. And I talked to a lot of developers who, some don't even realize this is an option because they just work as a front end and they get their REST API from the back end team. Put the database on the device and you really start to eliminate all of these problems. So then you can synchronize across the entirety of this database topology, from the embedded database to the cloud database and ultimately edge data centers, keeps the entire ecosystem basically consistent, okay? If in sometimes eventually consistent, but always consistent. And then finally, leveraging the private area network, should any of these other connections be interrupted, we can leverage the personal area network for peer-to-peer synchronization between the client databases. So if the data changes on one device, it's shared with the other local devices via that connection. So it's this architecture that ensures the lowest latency, highest availability, and most stringent data governance for applications by capturing and syncing data from cloud regions down to edge zones and ultimately on device. So you can also isolate data with precision anywhere in this topology, if you have the right database, of course, to ensure data privacy for applications. Sensitive data, again, never has to leave the edge. Now we put the logo over the diagram. You probably saw this coming. So Couchbase is a database that fits into this edge architecture, fits it like a glove from end to end. For the back-end database, you can deploy Couchbase in the cloud and at the edge. And for on-device data processing, you embed Couchbase Lite. That's our embeddable version of Couchbase. And data sync stitches the whole thing together so it all stays consistent. But if any part, any layer of this topology goes down, downstream clients are unaffected and continue to operate. Okay? And this is how you ensure that low latency, data integrity, and high availability. So far, hopefully making sense. So the Couchbase mobile product stack is made up of these three foundational components. So Couchbase Server, this is our flagship distributed NoSQL document database server, and it's got built-in support for SQL. That's not what, you don't normally find that with a document database. We wanted it to be very easy for relational developers to adopt a NoSQL database. So that's why we did that. We have built-in vector search also, along with full text search and eventing. and columnar analytics. This makes us a multi-purpose database that can be used for a variety of applications, including, of course, mobile. And then there's Couchbase Lite. Here we are. So this is the embeddable version of Couchbase for mobile and custom embedded devices. Also, Couchbase Lite supports vector search. So for those that might not be familiar, vector search is really the means to engage a database with AI, to basically connect them up. Vector search is the heart of similarity search and semantic search and image recognition and RAG, for example. We do all of this. And then finally, Sync Gateway sits in between, is responsible for secure data synchronization, routing, and access control between mobile clients and server tiers. And these can be deployed two ways: fully managed, as I mentioned, with Couchbase Capella, or self-managed. This is where customers would install wherever they want, on a self-managed on-prem, on their own cloud instance, on a cloud edge service like AWS Wavelength, their Outpost, or Local Zone. And essentially, this is what the entirety of our edge support is built out around. So if we, let's see, there we are. So let's dig into the topologies for a moment. So essentially, our self-managed tool sets are Couchbase Server and Sync Gateway that I just mentioned. But if you go with our managed and hosted, we have our database as a service. Under the covers, Couchbase Server, right? Except we're doing the driving for you. We manage it, handle the upgrades, et cetera, for you. And then for Sync Gateway, if you don't want to install it and manage it yourself, we have app services. That's entirely hosted as well. So we kind of see three access patterns here, and I'll just go real quickly through them. Offline first sync is where a device with the embedded database would run in isolation and synchronize securely through our WebSockets-based protocol app services. Again, Sync Gateway under the covers. For instances like mobile clinics, where you need to collaborate in isolation, a group, this is another actual customer implementation, peer-to-peer with Cloud Sync. And this is where groups of devices with Couchbase Lite can actually synchronize without a centralized cloud control point using peer-to-peer discovery technology. And then when there is connectivity, leverage that WebSockets-based synchronization back into Capella. And then also we have browser, desktop, and mobile apps. You can choose to use Couchbase Lite or not, and this is all accessed via a secure REST API. All right, Couchbase Lite. I'm only slightly biased, but I think it's the most full-featured, developer-friendly, NoSQL embedded database on the planet. With native support for iOS, Android, and Windows platforms, desktop and web server apps can be built with .NET and Java. We've just come out with JavaScript support for React Native, and our C API allows developers to build applications in C that run on nearly any embedded platform. So Couchbase Lite allows our customers' development teams to leverage SQL, even though it's a document database, and use our simple-to-use APIs for database CRUD operations, and comprehensive platform and language support that I just talked about that allows us to confidently make the claim: any platform, any language, any device. If you want Couchbase Lite to run on it, we can do that. All right, now let's get into the meat of the matter. All right, so now let's get into the background on what we did. Our engineering team recently decided to see if they could actually build an application architecture that would work anywhere, regardless of spotty or unavailable network connectivity. So to break down the fundamentals, an edge architecture requires these four components to deliver on promises of low latency, 100% availability, and data consistency. A cloud compute environment, an edge compute environment, a network connecting the cloud and the edge, and of course a database that can take advantage of the previous three attributes that syncs between the cloud and the edge. That's all you need, and then you can put together the pieces to actually build out that architecture. So what did we go with for each one of these pieces? The Ask stack, essentially. AWS, the world's leading cloud infrastructure provider. We used AWS Snowball as well. And this is a service that provides a secure, portable, rugged device that's about the size of a suitcase that we see here. And it runs AWS infrastructure, except you just bring it. It's portable. You bring it with you to the edge. And then we used SpaceX Starlink. This is the next-gen satellite internet service made up of constellations of low-orbit, small satellites. And customers connect to the network using a portable dish that we see here. And finally, Couchbase Capella. This is our fully managed cloud database as a service and includes that app services and Couchbase Lite. So a little bit about the effort. It was an independent test done by Couchbase Engineering. And we wanted to measure the difference in overall response times and bandwidth usage. We just chose those two as important metrics. And we wanted to do that when accessing a web service powered by Couchbase and deployed in the AWS US East region and deployed on an AWS Snowball device. So we'll take those two different environments and measure it out. So we had Couchbase Capella and Couchbase App Services in the cloud, Couchbase Server Sync Gateway deployed on the Snowball device, and Starlink was our network internet, and the client was a MacBook Pro on a local area network. So here we can see the basic architecture laid out. AWS Snowball Edge provides the computing infrastructure at the edge, and Couchbase is deployed to the Snowball Edge device for local data storage and processing, here on the right. And Couchbase Capella is the hosted backend database service in the cloud on AWS in the US East region. And Starlink is that connector from cloud to edge. So, we ran 4 tests. Essentially, a write of 1,000 docs to the edge from the client, a sync, which is different than a write, a sync of 1,000 docs from Snowball to Capella over Starlink, a write of 1,000 docs from Capella to client, and a sync of 1,000 docs down from Capella to the Snowball device. And we measured latency, and for synchronization, we measured the amount of data sent over Starlink, right? That's where bandwidth is precious with Starlink. All right, now for the results. So we expected to see lower write latency due to the local data processing, but man, it was substantial, right? The results show that the edge architecture reduced latency by 98%. Makes sense, right? The data doesn't have to go as far, and we've eliminated the internet from the equation. But we were also really excited to see the reduction in data sent over the Starlink network for data synchronization. And this was because of efficiencies that we've enabled through our synchronization protocol, like cross-record compression, delta compression. This means that if one field changes in your data, why send the whole document? We'll just send the delta, just that one field. That really narrows that amount of bandwidth that you need to actually use. And syncing updates over the edge architecture reduces the amount of data transferred over Starlink by 42% as opposed to using REST calls in a cloud architecture. And when talking about Starlink, this is really critical because it's shared bandwidth, right? And speed and availability can vary from time to time and wherever you go. And while 42% is really good, we think, continued tests under heavy load, we think we'd even see much better than this. And that's because the stack reduces the amount of data sent over the network due to the fact that sync is highly compressed, as I explained a moment ago. And the stack makes apps perform faster because local data processing, simply put, so there's less distance for the data to travel, and so we see the much lower latency. All right, so this stack and similar topologies can support a vast array of extremely remote computing use cases. So we'll bring the presentation back full circle here. And hopefully it's showing up. You can't really see it too well, but this is supposed to be our oil platform. And on the oil platform, they can process and analyze data by leveraging that on-platform edge data center, right? The Snowball device. And Couchbase is installed on that device and syncs data to Capella via Starlink. And if there ever is no connectivity, no problem, because the database is on the platform those apps continue to work as intended. For the in-flight airline apps, thanks to in-cabin data processing and storage, the crew gets immediate access to passenger information, profiles, preferences, and meals. Amenities and duty-free item meals are never oversold. And that helps make the customer's experience much more enjoyable. And it engenders that loyalty that, again, the airlines are highly competitive. This means everything to them. And for the cruise lines, the Ask Stack can provide the means for capturing constantly changing guest data while at sea, and using it in real time for offers and recommendations that lead to better guest engagement and the all-important upsell. So the customer that I've been referencing here, we have customer Royal Caribbean and Carnival Cruise Lines, by the way. They're not using Starlink just yet, but they are using an onboard data center. So Snowball is not the only AWS Edge service that we've worked with and tested. That was just the latest one that we did. We've proven out edge computing architectures with other edge services from AWS. I mentioned Local Zone and Outpost and Wavelength, where similar tests showed similar amazing reductions in latency on app reads and writes. And these edge services make it easy for customers to spin up edge infrastructure, right? No longer is building edge computing just for the most giant enterprise with the largest IT department. Thanks to AWS, they make it very easy for anyone to adopt very complex edge topologies and edge architectures. All right, so those are my planned remarks. I wanted to mention also on my way out, if anybody here is affected by MongoDB's deprecation of their mobile capabilities, Couchbase is here to help, just saying. So with that, those are my prepared remarks, and I don't know if I have any questions, but happy to entertain any.
Thanks, Mark. Thank you, Mylan.
Sorry.
That's okay.
Thank you for your instruction there and a little slam at MongoDB. We have time for a question here. Bibi, please.
Yes, definitely. Oh, hold on. Hello? Can you guys hear me? Cool, perfect. All right, so let's start with one question. With services like Starlink, does it mean there's no more edge?
Interesting question. No, definitely any time that you're computing, when you have applications that need to work sort of in a remote area, that will always be the edge. But again, I want to take this notion out of the talking track that remote means somewhere in the middle of nowhere. Remote can be in the subway in the middle of Vancouver. Remote can be in the air on a plane packed with passengers. So Starlink can be a huge help for that. Starlink is fantastic, but it can also have times where it's not so, where it's fallible. It can go down. So the edge computing architecture, being prepared for that and building for that inevitability of a lack of connectivity is really the way to, and that will always be kind of the epitome of edge, if you will.
Perfect. Thanks, Mark. Thank you very much.
Thanks, everybody.
Please thank Mark.